In this video, we're going to talk about enthalpy of formation and what it is and how it is used. So enthalpy of formation is interesting because when we do a formation reaction, the enthalpy, this is kind of the basis of doing enthalpy. So let me show you a formation reaction, and that way I can apply what these things are. Okay, so a formation reaction is going to be when we make water, H2O, okay, and so let's make it liquid, okay, from H2 gas plus 1/2 O2 gas, okay? And so the point is that when we do a formation reaction, the products need to be just 1 mole. The coefficient here has to be just 1 mole. Okay? And then the 1 mole of product is always made from its elements, and just its elements, in their most common standard state. And so things like knowing the diatomic elements, like hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, fluorine, Hunkelbrief, and then there's also oxygen, so then, that's part of it. And if this coefficient is going to be 1, that means we only need 1 oxygen, so we need a half here. So typically up to this point, we haven't really had to deal with coefficients of being a half, but a lot of times in thermodynamics, we will put halves in as the coefficient because we want 1 mole as the product. And so what is the reason for this? Why do we worry about this? Why do we worry about enthalpies of formation? Well, we worry about enthalpies of formation because what we want to do is we want this enthalpy, that delta H, to be the only one that we're worried about for 1 mole. Now what do I mean? If you go to a thermodynamic data table, and let me pull one up here, okay? So here's thermodynamic values, and you can find one in the back of your book or wherever. But if you look at any element in its most common natural state, ground state, standard state, like here's aluminum, okay? Aluminum has a delta H of formation, that sub F stands for formation, of 0. Okay, we'll worry about delta G later. Okay, so we can go down through and we can find any element in its most common standard state, its delta H of formation is 0. Okay, there's cadmium, calcium. Okay, I think you get the idea. Okay, for carbon, its most common standard state is solid, but as graphite. So now when we come back here, let me say that for that reaction, H2 gas plus 1/2 O2 gas reacts to form H2O. Now, if that delta H of H2, that delta H of formation, is equal to 0, and this delta H of formation is equal to 0, well, the delta H of formation, the only delta H of formation, or the only delta H that is contributing to the enthalpy of the reaction, is that of water. Okay, this is the only thing that has enthalpy. Only thing. Okay, so if this is the only thing that has enthalpy, enthalpies of formation or formation reactions become important because now we can line up a whole bunch of formation reactions in order to do a Hess's law problem. So a lot of times we do the formation reactions followed by a Hess's law problem. Okay. So So it says, write a formation reaction for FeCl3 solid and for sucrose. Okay, well this should be a fairly straightforward reaction. Remember, we want to form 1 mole of product. So when I do this, I typically start with the product in whatever state I want it to be in. And now iron, F, is going to be a solid. And then chlorine is Cl2. It's one of the diatomic elements. And so it's found as Cl2, but how are we going to get these equal? You're going to make this a 3 halves, or a 1.5. So it's iron plus 3 halves Cl gives us this, and this should be a gas. Okay. What about for sucrose? Sucrose, table sugar. So again, we're going to make sucrose, so it's C12H22O11. So again, it's carbon, solid, but it's solid graphite. It's not solid diamond or Simon. There's even something called buckyballs. Okay, Buckminster fullerene. Okay, so that carbon is, there's 12 of them. Plus, let's see, so H2 gas, well, we have 22, so we need 11, and that's its most common natural standard state. H2, it's diatomic, plus, and I'm going to run out of room, but I'll still figure it out, plus O2 gas. Now we have 11 here and 2 here, so this has to be 11 halves. Okay, so that's going to end up equal 11, or 5.5. You can use either one. Okay, so that's how you write formation reactions, and these become powerful when you're trying to solve for Hess's law, because all of these things, again, all of these things have 0 for their enthalpy, so the only enthalpy that is contributing to the overall reaction is that of the product. Okay, that's why we write formation reactions. Couple that with Hess's law, and then you can find all sorts of enthalpy problems out. So, anyways, that's Hess's law. That's formation reactions.